The Canadian Society for Chemistry operates under the umbrella of the Chemical Institute of Canada. And so this presentation, this panel discussion is brought to you jointly by the Chemical Institute of Canada, the local section, run by Vance Williams as president over there, and by Simon Fraser University. So we thought it was our social and moral obligation to present a balanced and informed view of nuclear power, the crisis currently occurring in Fukushima, and to discuss some of the implications of that crisis. So we have gathered together a panel of experts, and Simon Fraser University happens to have a specialization in this area of research. We have a very strong program in nuclear science. So before I get to the introductions of the panelists, let me just take this occasion to let you know that this coincides with one of our events for the International Year of Chemistry that's taking place nationally. We will soon have a stamp that's been issued by Canada Post commemorating the International Year of Chemistry. And it also happens to coincide with the Year of Science that is taking place provincially, and that's run by the Ministry of Advanced Education. So with that, let me introduce our panelists who will entertain you tonight. Paul Schaffer, the Deputy Head of Nuclear Medicine at Triumph, and also an adjunct professor at Simon Fraser University. Next to him, Mark Jaccard, who's a professor in the School of Resource and Environmental Management in our Faculty of Environmental Sciences. In the center, we have the moderator, David Murphy, who will try and control you in case you get unruly. Next to David, we have Corina Andreoiu, who's an associate professor at Simon Fraser University in nuclear science, and Kris Starosta, to the extreme right, also an associate professor in nuclear science in the Department of Chemistry. So before we proceed, I would ask you all to turn off your cell phones out of courtesy to the speakers and the panelists. And they will try to be brief, but they will impart some information to you. So with that, ladies and gentlemen, I will hand the proceedings over to David Murphy, who's a senior lecturer in the School of Communications, who will be our moderator this evening. David, thanks.
So to begin tonight, I would like to just mention that one of our mandates at SFU is to inform and engage the public around issues that are of importance and timely, such as this nuclear energy crisis that we're experiencing now. The informing part is something that we do every day, that when we teach and when we instruct our courses, but it's the engagement part that I think is most important for a panel like this. And engagement implies a dialogue or some kind of interaction. So I believe that it's your role here as an audience to help us with this and tell us what you think and what your perceptions and your ideas are around nuclear energy and the crisis that we're faced. We're going to get a lot of information tonight from our panelists, and I think one of the reasons why I was invited to speak today is because I am not an expert on nuclear chemistry, whereas everyone else here is. So if I don't understand what's happening, then chances are there are other members of the audience who don't understand what's happening. So I will be trying to moderate this discussion a little bit to make it more comprehensible to scientists and non-scientists alike. I would like to say also that there's a lot of information out there around this topic. There's a lot of sources that come to us, like news sources, which tend to be sensationalized. There's public relations campaigns that are coming from the nuclear power industry itself that is trying to reinforce the idea that nuclear energy is safe. There are government statements and statements from companies that are involved directly with this crisis. And a lot of this information is conflicting and confusing. So this creates in our environment quite a difficulty in assessing the risks. And what I'm hoping tonight is that we'll be able to present to you something that is a little towards a objective perspective on this situation. So our 4 panelists tonight have quite a broad range of experience and specialty in their fields of study. And I'll turn over to start with to Dr. Mark Jaccard to begin our discussion.
Thank you. Now we have very limited time to speak, and I don't think you should include the time that I take trying to get my talk up here. Oh, I guess we're good. Okay, 7:15. So actually, David already gave you one piece of misinformation. He said he's got 4 speakers up here who know a lot of chemistry. He doesn't. Maybe he has 3. So I'm an economist, and I have some training in ecology, but basically I'm much more on the social sciences side. And in that regard, I also welcome the idea that we try to provide independent information for the public, and I was certainly involved in that during the time of debates over British Columbia's carbon tax, but it didn't leave me with a lot of hope for for the public to get a real idea of what the particular issue was and what the facts were on the ground. But anyway, I'm going to give you the broader sense of nuclear energy and how it is one of our energy options, and how people look at it in my field, which is energy systems analysis, looking at the global energy system. What are our options? What are the risks and impacts, costs of these different alternatives? And I'm going to just go through 10 slides that give a bit of a feel for those issues. And so I'll do that right away. So there's about 440 nuclear power plants operating today, and they're about 83% in the OECD, the Organization for Economic Cooperation and Development, richer countries. But that's only 14% of the global electricity generation. And electricity is only part of all the energy we use, so it's only 3% of the human energy system at this point. That's 375 gigawatts. Well, a watt, 60-watt light bulb, or 15-watt light bulb if it's sufficient. The way to compare this is the British Columbia hydropower system is about 10 gigawatts. So the total nuclear installed capacity, about 40 times on the planet, what we have in British Columbia. And it grew a lot in the 80s, 90s, I'm going to show you on a slide, but it hasn't grown much in the last couple of decades, growing only about 2 gigawatts per year net if we include the older plants that are starting to close. There are 65 plants under construction, and about almost half of them are in China. So just look at the blue line there. The red one is terawatt hours or kilowatt hours of electricity generated, but the capacity that we've installed is that blue line. And again, it shows you that climb from 1980 through 1990 up towards the 375 gigawatts that I was just telling you about. But you can see very little net addition, very slow rate of growth since then. And there's a talk about our nuclear renaissance because we need greenhouse gas-free electricity. But will that actually come to pass is the big question out there that was out there before Fukushima and is still there afterwards. Here's a breakdown internationally. So you see that 100 of those gigawatts are in the United States. France has about 60 of them, and then it goes down to Japan, Russian Federation, Germany, and you can see Canada's about the same as Ukraine. But we have more than the United Kingdom and in Sweden, and ours are almost all in Ontario. What are the risk challenges? So, okay, we just talking about one, minimizing reactor accidents or minimizing the effects after those accidents occur. Safe disposal or storage of either of the spent fuel or any other radioactive waste, and preventing proliferation of nuclear weapons. So that's a very simplistic breakdown of 3 key aspects of risk. As an economist, we also talk about what are the implications for nuclear power from an economic point of view, i.e., If you invest in that, if you put your eggs in that basket, what might it cost you? What are the Japanese looking at today after an accident like this? Are they going to go back through all of their existing plants now and refurbish them, and at what cost? So there's some big issues there. So rising costs due to operating plant safety concerns. Rising costs because we still haven't really, and other speakers can speak to this, figured out how to permanently store the waste. We have some ways of recycling, some ways of storage, but we don't really have a permanent way of storage, which is a big issue in my view. And then, of course, the rising costs of how to make sure that our knowledge about nuclear power doesn't lead to nuclear weapons development. And then possibly fuel supply constraints, like the uranium, but I'm not convinced that that's as big an issue. So now, the global picture, my last few slides. So nuclear is, as I say, about 3% of global energy. So our global system is still 85% fossil fuels, that combination of coal, oil, and natural gas. So what are we going to do about that, right? We only have, in terms of climate change risk, one of the many risks out there, but a really big one, we either have to stop using fossil fuels, which means switching to nuclear and renewables, or if we're going to use fossil fuels, we have to get the energy out of them and capture the carbon and not let it get into the atmosphere, somehow store it. And then we've got renewables, which represent about 12%, but much of that is still our traditional use of biomass, so burning it in developing countries for cooking, even some industrial uses, a lot of hydropower, and then smaller amounts of uses of geothermal, wind, solar, and ocean. And even though all you ever hear about is all the investments we're putting into solar and wind power, they're still minuscule as part of the global energy system. And finally, the one other option out there, besides nuclear, fossil fuels, and renewables, is energy efficiency. I mean, we humans are not angels. We use materials and energy, and we're going to keep doing that. But can we use them more efficiently? Can we accelerate the rate at which we have become more efficient over time? So those are kind of the options that we always look at in the game that I'm involved in. And how do we compare those options? Because guess what? All of the options, all of them, we used to talk about, well, there's clean energy or green energy, but really, all the options have impacts and risks. And so the really difficult part is we have to try to figure out how to compare these impacts and risks and the costs while we're figuring out which way we should go in a particular jurisdiction for the energy forms that we most want to favor. And so just to give you some sense of the relative magnitudes here, the Chernobyl accident in the Ukraine in '86 should cause, the forecasts are in total over time about 10,000 deaths from cancer. It's already caused many, but that's an estimate of what the total would be. Coal combustion in the United States alone causes 10,000 deaths per year from respiratory illness. And actually, our use of fossil fuels causes about 2 million deaths per year from all aspects of fossil fuel use, and 6,000 mining deaths per year just from coal mining itself. So that 6,000 is worldwide, and the 2 million is worldwide. Just to give you a sense of these relative magnitudes. And of course, we have that risk of climate change from fossil fuels, and then we have issues okay, let's just go to renewables. Aren't they the clean, green form of energy? Well, hydro dams collapse or silt up. Biomass, well, what does this mean for the land that would have gone to food production or for biodiversity? And what about other issues, wind, geothermal, tidal, and so on? And then we have these special challenges facing nuclear, though, which I'll just focus in a bit. We've already got that. I just mentioned it, the climate risk. We have a problem with renewables because they're intermittent. We need electricity at a certain time of year, January 23rd at 4 in the afternoon, the system's peaking out. If we've got a lot of renewables in there, let's hope the wind is blowing or the sun is shining or water is flowing or whatever it is we need to have happening. Biomass, I talked about that risk, and then most renewables being low energy density, then we've got substantial land or water use implications. So here in British Columbia, we have a moratorium on nuclear power. We have now said that for future electricity generation, we want 100%, well, it's actually 93% for some bizarre reason, but basically that's 100% zero emission forms of energy. So in British Columbia right now, we're rapidly developing run-of-river hydro. And run-of-river hydro is intermittent, so it has other issues, but also it has some real water use and land use issues for people. And so it's not just a clean form of energy. So those are the kinds of trade-offs that are out there for all of us. I'm going to end 3 slides, I hope I'm on time, with just to give you a sense of how we then try to take into account, people that do what I do, these diverse elements, characteristics, risks, impacts of our energy options out there. I'm involved in the Global Energy Assessment, which will finally come out with its major report here in the next year. We've just been finally sending it to Cambridge University Press. It's a ridiculously huge project, but there are smaller technical summaries and summaries for policymakers. It's to sort of map out our options for a much more sustainable global energy system. And it's taken up a lot of my time for the last 3 years. I'm the convening lead author for sustainable energy policy. So I lead an international team, but there's whole bunches of teams. So it's run by the United Nations, major governments, and major international organizations, and it's based just outside of Vienna at IASA, the International Institute for Applied Systems Analysis. And its goals are energy access, so we still have 2 billion, or 1/3 of humanity that doesn't have electricity, and another 2 billion that really just get it in an intermittent way. So basic services, and that it be affordable, energy security, and of course the health of humans and natural systems. And we can't completely rule out catastrophic things happening. A meteor can hit a nuclear power plant and have some effect. I don't know if that would matter, but we can never rule them out completely, but we're trying to have a low risk energy system. So we develop a bunch of scenarios, and I'll just show you a couple of slides of that and be finished so that we're on to the next speaker. We look forward to like 2050 and 2100. And no, don't look at all this, so I've drawn some red circles around that. So we've done different runs, see the restricted portfolio pathways, where we might have no CCS, no carbon capture and storage, right? So, that means we're going to really have to switch away from fossil fuels, because only with carbon capture and storage could we use fossil fuels and still prevent dramatic climate change. Same, we'll look at bioenergy, and so we'll do scenarios. So we have done scenarios with no nuclear. And so we do have enough fossil fuels out there for a very long time. We have capacity to do renewables to meet a growing energy needs of humanity. But they're very expensive, they're very challenging, and they have their own risks associated with them. So you could have a future without nuclear. You could decide we don't need nuclear in the future. And so we've run scenarios like that. So I'll just give you an example. Just look at yellow. I thought it was yellow. The colors have changed. Oh, okay, nuclear is kind of green here. Mustard then. So this is one in which nuclear is phased out. See, we're looking, and the global energy system, our energy services grow like this, but all of this is efficiency. So this is a radical efficiency effort. So I had to try to cook up all the policies for that to happen. It's quite draconian compared to what you have in BC today. You know, you're not buying another light bulb that isn't incredibly efficient. And this is renewables. This is solar. So, I mean, this is for some people, this is an ideal world, policy-wise, very difficult to do. But you've got other ones where here, nuclear has this big growth, and 2/3 of the plants are in Asia. And finally, here's one where it's even larger, the nuclear wedge here. So this is but we're phasing out oil, or, you know, we're looking at these different scenarios, and we record what their likely costs might be, and so on. So, final slide. Post-Fukushima, what might change? So remember, as I've said, all energy options have impacts, risks, and other challenges. Cost, accessibility, how do we integrate them in the whole system? Fukushima, for an economist, will definitely increase nuclear costs. So there's going to be extra expenditure on safety. And this is something you probably know, but a few people would know. To make nuclear work, governments actually put a limit on the liability of nuclear plant operators in the case of an accident. So in the United States, there's an act called the Price-Anderson Act, which limits at $12.6 billion, is the latest number, the liability of a private company running a nuclear plant in the case of an accident. So in other words, we've basically socialized the risks of nuclear. We've said we'll take that over. So that's something to think about. So Fukushima may slow or halt development in some jurisdictions. This is me now. But I think it's in a predictive sense and is unlikely to cause a wholesale halt for nuclear, that there'll be some growth likely. And where would that happen? It would most likely happen in countries with rapid growth of energy demand and high-cost alternatives, so China is an obvious example. Countries that have areas of low population density and other favorable siting conditions. I think Japan going forward, or Germany, even the United States, this is going to be a real challenge in the rich countries in future. And then also the countries that are not at risk for nuclear weapons proliferation. So you start to knock out certain countries about where nuclear could still grow. I don't think its growth is wiped out by Fukushima, but I think what was a restricted growth path in most likely terms anyway will become even more so. And I'll end right there. Thanks for your attention.
Thank you, Mark. I would say that we're going to save our questions to the end of the presentation, so please make notes of any questions you want, and we can ask the panelists at that time. I'd like to invite Dr. Corina Andreoiu to...
No, I don't... Are your slides on the...
So, yeah, I'm Corina Andreoiu, and I will say something about how reactors work, what they are and how they work. So, nuclear reactors. Nuclear reactors release energy from neutron-induced fission, and as any power plant, they will produce steam that that drives a turbine that produces electricity. And most of the reactors, they are classified in different ways, but most of them have the same kind of elements consisting of. So we have a fuel, which is natural or enriched uranium. We have a containment vessel to prevent escape of radiation fission products. We have a moderator to slow down the neutrons, and I'm mentioning this because sometimes you hear that CANDU reactors, for example, they use heavy water. They have shielding to prevent radiation from causing biological harm, a coolant to remove efficiently heat from the core, and a control system, which is rods made of a certain material that will eat or absorb neutrons, and they will halt the fission reaction, and several emergency systems. So here we have energy released in fission. We have a neutron interacting with or bombarding uranium, and it splits in different fragments which are radioactive. It releases 2 or 3 neutrons and some energy. And we usually hear about release of krypton, xenon, which are gases, or iodine on cesium most of the time. And the fission of 1 gram of uranium per day liberates about 1 million watts of energy. This is a huge amount of energy. And 8 pellets of uranium, each smaller than as a human thumb, will release enough energy to power an average home for 1 year. So that's why it's so important to use uranium. So the reactors in Japan are called boiled water reactors. They typically allow to boil water in the reactor core. They operate, the operating temperature of the reactor is about 300 Celsius, and they produce steam at a very high pressure. And current boiled water reactors, they come in different sizes, and they have different electrical outputs. So they range from 460 60 megawatts energy at unit 1 to a much higher output, 700 or thousands megawatts of energy. And they are not that efficient. They are only 33% efficient. So what are the concerns when we talk about reactors? One of the worst case scenario is when we have a reactor or a fuel meltdown. We can have loss of coolant accident. And in these particular cases in Fukushima, we heard about hydrogen explosions and spent fuel problems. Just this is a cross-section through the reactor. So here at the heart of the reactor, we have the reactor vessels, a vessel where the uranium rods are, and it's surrounded by steel and a concrete bulb-shaped building, which is very thick, and this is also referred as a dry well. And the purpose of this is to contain any release of energy in case of a loss of coolant accident, for example. We have secondary containment, which is also a very thick building. We have a wet well or a torus beneath the reactors, which is a suppression pool where steam can be released. It acts as an energy absorbent medium. And you heard also about the spent fuel pools. So here we have to refuel the reactor periodically, and the fuel is kept here in these pools until it's getting cold, and it can be shipped in a permanent storage. So this is an image or a cartoon of a core. So we have uranium rods grouped in bundles, and they are about 4 meters long. Each assemble contains about 60 fuel rods of uranium oxide with a zirconium alloy cladding. So they're inserted in some tubes made of zirconium alloy. And units number 1 to 3 contain about from 400 to 764 fuel assemblies. Number 4, the unit number 4 was empty of fuel because it was undergoing maintenance. And the other units 4 and 6 were shut down. So here are some numbers. Fuel meltdown happens at 2,400 Celsius degrees. Melting point of steel vessel happens at much lower temperature. Cladding oxidation begins at 1,200 Celsius degrees, and cladding melts at about 2,000 degrees. So this is just to put in perspective what can happen at these temperatures. The spent fuel pools, which are here, are used to store spent fuel. And here you see the numbers of fuel assembles in each fuel pool, in each unit, and I will draw your attention to number 4, which was quite on the heaviest side, so 1,500 fuel rods. The pools are quite big. They can be 12 meters deep, and 7 meters of water covers the fuel. This is for cooling down, but also for shielding. Water is a very good shielding. And for example, at Unit 4, they estimated 3 megawatts thermal power at the time of earthquake. So this can boil about 115 cubic meters per day of water, or 100,000 liters. So they have to be cooled down permanently. The pools normally operate at 30 Celsius degrees, and they are safe up to 85 degrees. Unit 4, I think, at some point reached 84 degrees Celsius. And there is also a central fuel storage with a very huge capacity. So this is the reactor core where the uranium is hosted. So water is boiled here in the core. It produces a lot of steam. The steam is taken through this primary line, steam line. It goes into the turbine. It drives the turbine, and then it condensates here. So heat is taken to the river or to a huge body of water, and then the water is again heated up and goes back into the reactor. A torus, or the suppression pool beneath the reactor, it normally operates at ambient temperature, so it removes heat which is released in an accident, and large quantities of steam from the reactor vessel can be released here, and this way the pressure goes down and steam condensates here and reduce the pressure in the main circuit. But when the temperature in the torus heats up to 100 degrees Celsius, the system becomes ineffective. There are several emergency systems, and the residual heat removal system operates when the reactor is shut down, and this is a secondary circuit. It circulates water from the pressure vessel to the heat exchanger here, which transfers heat to the sea and is driven by electrical pumps. There is another emergency system called emergency core cooling system, and it's also operated by electrical pumps. It draws water from the torus, or the suppression chamber, and the water storage tank. And there is also a core spray system, which is operated by a turbine that is operated by heat from the reactor, but all require a different degree of electrical power. So what happened? Daiichi was upgraded in 2008 to withstand a huge a relatively decent earthquake, magnitude 9, but on March 11, the earthquake was much more powerful in a certain direction, and it lasted about 130 to 150 seconds. Also, the design basis for the tsunami wall was 5.7 meters, but the tsunami height reported after was about 12 to 14 meters. So in the end, the combination was fatal. Fukushima nuclear plant, it has 6 boiled water reactors, and it's one of the top 25 nuclear power plants in the world. So reactor 4, 5, and 6 had been shut down prior to the earthquake, so for maintenance, and units 1 to 3, when the sensor sensed this huge earthquake, it stopped. The reaction, the fission inside the core stopped. This is an automatic shutdown. It's a normal scenario for any plants. Daini stopped completely, and this is called scram. And energy generation stopped as well, as I said, stopped. But the reactor cores will still produce huge amounts of heat after the shutdown because the heat which is accumulated in the fragments, in the fission fragments. So after a week, units 1 to 3 can boil away 230 to 380 tons of water per day if all external circulation ceases. And these heat productions will take half a year to halve. And this is illustrated here in these graphs, which shows the power in watts as a time after the shutdown. And you can see this is only for 1 megawatt reactor. And here you see after 1 hour after shutdown, you still have 10 to the 4 watts from a 1 megawatt reactor, depending how much it was operating. So it will take quite a while to cool down the reactors. What happened is that the residual decay heat can induce really high temperature in the core, and the steam produced in the core will interact with the zirconium cladding, and this is an exothermic chemical reaction, so it will release heat. This is not a nuclear reaction. So we have cladding interacting with hot water. It will release hydrogen gas, and if there is no pressure release, we'll have an explosion. So what happened? Immediately after the shutdown, the auxiliary cooling system driven by electrical pumps started. Emergency diesel generators worked for about 1 hour, and they were flooded by the tsunami. They were equipped with some battery power, but these are insufficient to drive the residual heat remover system, and they've been depleted in about 8 hours. So without heat removal, a lot of steam has been produced in the core. The pressure went up, the temperature went up, the pressure went up. There was no cooling, so things escalated. So we had hydrogen explosions. For units 1 and 3, this removed the top part of the reactor buildings, and at unit 2, this might have taken place in the torus, causing damage. We had core damage for units 2 and 3. Containment damage was suspected for units 2 and 3. And after the total failure of cooling systems, seawater has been pumped into the core reactors of unit 1, 2, and 3 to prevent overheating and further core damage. The whole situation has been worsened by the spent fuel pools, and while Fukushima 4, Daiichi 4 was fully defueled for maintenance, it suffered a loss of seawater pumps and electricity rooms, so the cooling of the ponds were insufficient, and this also caused some damage. We had water-boiled hydrogen was produced by the interaction of water and hot fuel, and the hydrogen explosion wrecked the building. So 2 days after the earthquake, with a lot of effort, and the three reactors were stable or relatively stable, but still not in cold shutdown. Cooling was provided from external sources using freshwater and pump trucks. And at that time, the accident was classified as level 5 on the International Nuclear Event Scale, as an incident with wider consequences, the same as 3 Mile Island. But now it looks like the accident was classified at level 7, which is the same as Chernobyl, because a lot of radiation has been released, and it has a huge impact on the population. So now we have a level 7 incident, and this will be for sure in textbooks from now on. Most of my information comes from World Nuclear News. I will use cautious where you read things, and you should stick with trustable sources. Thank you.
Thank you. I'd like to invite Kris Starosta to speak now.
Thank you very much. So I'll switch gears a little bit, and I'm going to talk about the monitoring of the radiation levels in the Pacific Northwest, although I should make a disclaimer, and I'm going to mostly concentrate on the measurements which have been done at SFU, and so this does not cover all the monitoring which has been done. So just to start, there is a few information about nuclei which we need to review before we go to the releases to understand how the different isotopes which have been released come about. So as you know, the nucleus is this small thing sitting in the center of the atom. This is not to scale, this is very tiny. If the atom is of the size of a football field, the nucleus is the size of a marble. Nuclei are made out of 2 kinds of particles, protons and neutrons. You don't take from that protons are red and neutrons are blue, that's just a color code. But what is important is that there are 2 different kinds, and periodic table of elements which you know from chemistry in nuclear science is extended into 2 dimensions. So these are the combinations of protons or neutrons which are stable, which exist. There is something like 3,100 identified so far, and these are color-coded by lifetime, or on how long do they live. So the black ones, which you see here, are so-called stable nuclei. These are nuclei which we are made of, and there is something on the order of 250 of them. Other ones are not stable, and the darker they are, the more stable they are, or the lighter they are, the less stable they are, and they decay quicker. One important concept also which we would like to review here is the nuclear half-life. And the nuclear half-life quantifies how much of the substance is left, radioactive substance is left after a particular time. And here's a cartoon. Let's assume that we have some storage where we keep containers with radioactive fuel. After a half-life, half of them is still full and the other half decayed. So you have half of this amount. After another half-life, you have half of this, which is left. And after another half-life, half of that. And after another half-life, half of that. If you take it, what you can take from this is that apparently you need to wait for infinite lifetime for this to decay completely. Although, yeah, that's true. Although on the other hand, if you reduce something up to this level, it stops to be significant. And the half-lives are different depending on different isotopes or different radionuclide. And for the 3 which I'm going to talk about, iodine-131, this is 8 days. For cesium-137, this is 30 years. And for plutonium-239, this is 24,000 years. So these half-lives can be very different. Corina mentioned the fission reaction. So we take a big nucleus, we give it a neutron, it becomes excited, has energy, splits into smaller fragments, emits other neutrons. And these are these fission fragments which were formed, which are the radioactive nuclei which we are talking about. And here is again the same chart. And these are the fuels of nuclear reactors. So this is uranium-235, which is fissile. This is actually not a good fuel. It's not fissile with thermal neutrons, but it's so dominant that usually we have always uranium-238 in the fuel. Another fuel which is used is polonium-239. So you have these heavy elements which you split, and what you produce are these fragments here, which are called fission fragments. So if you ask me what is released, this is what is released, and there is a lot of this stuff. You can see the color code. The more dark, of course, indicates higher density. Sorry, higher percentage. And if you take this map and you compare with the other map, you can see more or less where the lifetimes are. And you can see that some of these fission fragments are very short-lived, but some of these fission fragments are actually close to the stable lines of stability, and they will decay for a long time. And that's the problem of nuclear waste, which Mark was mentioning in his talk. All right, so what happens to the fuel? In the reactors which use uranium in the fuel, usually you have a low enriched uranium fuel which contains 3% of uranium-235, which is fissile, and 97% of uranium-238. And this is the fresh fuel. Then you run it in the reactor, and then you have a fuel which is consumed or doesn't contain uranium-235 in such quantities. And this fuel is different. It has 95% of uranium-238. It has 1% of plutonium. It has 1% of uranium-235 and has 3% of the fission fragments. And if you have a reactor accident, all this in principle can be released. This is the cartoon which shows you the production of plutonium. Essentially, you have fission reaction, which Corina was talking about. In some cases, uranium-238, which is present in the fuel, can capture a neutron and then by the beta decay turn itself into plutonium-239. So 238 plus a neutron makes a mass 239, and then subsequent beta decay makes it to polonium-239. 239. Why polonium has been so discussed? So polonium is a man-made radioactive element. It's a heavy element containing 94 protons. Polonium-239 is produced in fuel containing uranium-238. Polonium-239 is actually the material of choice for nuclear weapons. The critical mass of polonium-239 is pretty low. There is a lot of polonium from Cold War sitting around, which was made to produce a nuclear weapon. And at some point, of course, because it is a fissile element, there was an idea of mixing polonium with uranium to make a fuel for nuclear reactors and actually burn polonium as a fuel instead of keeping the stockpile, which can be used, for example, for weapon production. So one of the reactors in Fukushima contained a mixed oxide nuclear fuel, which was a mixture of plutonium and uranium. The issue is that element of plutonium is actually highly toxic when inhaled. It's less toxic when ingested, but animal studies found that accumulated dose of few milligrams of plutonium per kilogram of tissue is lethal. And traces of plutonium were reported to be found at Fukushima a couple weeks ago. Then the reports about plutonium stopped, and there was no talk recently about any presence. So I think that the origin is unclear right now. But this is certainly a concern in the reactors which are using mixed oxide fuel. Another element which we are going to talk about a lot is iodine-131, called also radioiodine. It's also a man-made radioactive isotope. It has a half-life of 8 days. It is an abundant fission fragment. It is used for medical purposes. It's used in the radiotherapy of cancer, especially for imaging and therapy of thyroid cancer. It's not found in the atmosphere in normal condition. It's a very good indicator of radioactive releases from reactors, because the signal from iodine-131 is not obstructed by the backgrounds. The first thing you see, and you see it well. The concern about the radioiodine is that it can accumulate in the thyroid, and a large-scale exposure to 131 is potentially a health hazard. Another isotope is cesium-137. Its half-life is 30 years. It's also an abundant fission fragment. It's also used in medicine for cancer therapy. It's also used for food irradiation. An interesting thing about cesium-137 is that it was not present in the environment before 1940s, because only in 1940s fission started to be used for nuclear power releases. So any container which was closed, hermetically closed before 1940s, does not contain any cesium-137. It is one way to actually show that the content of the container has a history of more than 60 years or so. That's the way to prove it. It should not have any cesium. It was used to prove the genuity of some wines, actually. People were asking us a lot about the releases of cesium-137 from Fukushima, and the answer which I can provide today is that we are going to look for this, but right now we cannot see that, and the reason is that cesium-137 sits on the background from nuclear weapon explosions, and not everybody remembers, but until the Comprehensive Test Ban Treaty, there were on the order of 2,000 reported tests of nuclear weapons and 550 atmospheric explosions. And in 1961, there was 140 nuclear explosions in this 1 year alone. All right? So we see cesium-137, we see quite a lot of it, but we cannot disentangle the signal from Fukushima from the signal from the nuclear weapon tests. So what about releases? Releases depend critically on the accident scenario. Of course, what goes first are gases, vapors, aerosols. 3 Mile Island accident, which is one of the benchmarks, released gases only, released a lot of iodine-131. The Chernobyl, which is another one, had an explosions and fires, and these explosions and fires resulted in the release of 6 tons of fragmented fuel. And this 6-ton fragmented fuel was also accompanied by the release of radioactive gases. the release of iodine-131 from Chernobyl was 2.4 million times higher than from the 3 Mile Island alone. I think I should stress that the crisis management in Fukushima successfully prevented large-scale radioactivity releases in the past month. I mean, there were releases, there's no doubt of that, but it's not comparable to the releases of 6 tons of fragmented fuel from the Chernobyl. So how do we monitor the releases? We see for the signatures of decay, and these are the signatures in the high energy photon spectrum, and this is a spectrum of gamma rays, and this is energy. These are high energy light quanta, essentially. And you can see the very characteristic patterns. So for example, the blue pattern here is the pattern of cesium-137. If I see this pattern, I know I have cesium-137. If I see the red pattern, it's a different isotope, it's cobalt-60. So I see the pattern, I recognize the isotope. To do this, we use a detector which we have at SFU. It's called GEARS. It stands for Germanium Detector for Elemental Analysis and Radioactive Studies. And this is the detector alone, and what you see, it's mostly shielding. And the reason we need a lot of shielding is because there is a lot of radiation around us. And if people are telling you that there is a lot of radiation around you, it's true. Everything which is in red is what we see without the shield. Okay, this is the radiation which we as humans are getting on an everyday basis. And if you don't like the red spectrum, you are still getting it, okay? So now the blue spectrum is the spectrum which you see after you put all the shields, and this suppresses the background by the large factor, and it's a factor of 100 or more, and that's the suppression of the background was the reason we could see the signal. So I should give credits for sample collections and handling, and we collected the rainwater, and the SFU nuclear science students were instrumental, Aaron Chester and Rachel Ashley, in collecting the rainwater. And then we had people collecting seaweed, and we had a collection from North Vancouver by Ken Myrtle from SFU Physics, and then marine scientists from the Banfield Marine Science Center, David Riddle and Hannah Kuchera, who were sending us the sample of seaweed, and many other volunteers which were helping us. So here is the signature of iodine-131 in the rainwater, and the signature is this gamma ray line at 365 keV. And you can see that there are other gamma ray lines which are stronger than this. But what we see is that we don't see anything on March 18th, then we see something on March 20th, and then we see very, very little on March 29th. Based on that, we can draw a time profile. We can study a time profile of the content of iodine-131 in the rainwater. And we started when we learned about the Fukushima, so we started to measure ahead of time, and we haven't seen anything. And then you can see here an increase, and there was a couple of sunny days. Unfortunately, we missed the maximum, so there was somewhere here the maximum, but the sun was there, so we couldn't measure. And then you see the decrease, and over the last, let's say, 10 days, there was essentially unmeasurable traces of iodine-131, essentially nothing. These are the samples of seaweed which we were analyzing. The reason we analyzed seaweed is that seaweed actually bioaccumulates iodine-131, and it provides us with a good strong signal because it accumulates the isotope from water. So we were just drying the samples, dehydrating them, and grinding them into samples which you can measure, put close to the detectors. And here's the signature of iodine-131 in the North Vancouver seaweed, so nothing on March 15th, and then clear signal on March 22nd, and we can quantify the amounts, and we can draw a diagram again. And what you can see here is you have no signal in the seaweed on March 15th, and then it goes up, reaches the maximum, and decays. Here is a graph. Okay, so let me play this again. Okay, seaweed with water, seaweed with water. All right, and what you should get from that is that here's the water, and of course, water gives you a snapshot, right? Water gives you the instantaneous amount of iodine-131 on that day at that time when you collected the water. But what seaweed does, seaweed accumulates iodine-131, so it has a delay because it will accumulate from the environment, and you can see that. So here's the maximum of the rainwater, and here's the maximum of the seaweed, and I predict that because we don't see anything here, it will go down. Thank you very much.
Thank you. And our last speaker, Dr. Paul Schaffer.
How do I go back into presentation mode? Good evening, everyone. My name is Paul Schaffer, and I've been asked to come here today and provide some perspective on the health effects associated with the radiation that we've been detecting from the Fukushima reactor complex. And so what we're talking about here is the distribution of radioactivity from Japan through atmospheric, in this particular case, and eventually we may want to consider the water-based distribution of radioactivity from Japan towards the west coast of North America. So as Kris mentioned, we are continuously bombarded by radiation. And so with this presentation, I'm hoping to put into perspective what you saw from the previous presentation and what we encounter on a daily basis. So whether you like it or not, you are continuously bombarded by radioactive emissions from various sources. Half of our annual dose, and I'll get into specifics about what those numbers are in a bit, comes from our surroundings in the form of radon gas and other emissions from the ground. The buildings that we're in, such as the one here that's made of concrete and whatnot, contains radioisotopes more so than other buildings. So brick buildings have a larger proportion of radioactive isotopes in them than others, and so we receive a dose from those. Bananas and other high phosphorus foods contain radioactive potassium-40 that also give us a dose, but there's other radioactive elements as well in the food that we eat and in the drinks that we consume. And then there's outer space, constantly bombarding Earth. Earth provides a pretty good protective envelope around us, but that doesn't stop everything. So between all of these different sources, there's literally nothing we can do about those except move from place to place. So a place like Vancouver receives a dose of a certain level. If you move to Calgary, it's actually 4 times higher. And there are places in the world that are up to 50 times higher than Vancouver. So you can see natural background radiation is continuously bombarding us. Our bodies have adapted quite well at repairing the damage caused by this radiation. And so within this grand spectrum of things, you can see there is another wedge here that represents radioactive dose obtained from artificial sources. Most of that is associated with medical scans, dental x-rays, CAT scans, CTs, PET scans, you name it. That's my specialty in medical imaging. But within that wedge, there is a small percentage, less than 3%, that is associated with other sources, and then a separate category for nuclear power and or weapons testing, which you saw in the previous presentation. So hopefully that puts into perspective here exactly what we're talking about when it comes to receiving a radioactive dose from our surrounding. Now, when there's an accident, it's a matter of how much of this wedge here grows in size relative to everything else around us. So again, just to put it into more of a pictorial representation, from all around us, there are a certain number of cosmic rays continuously bombarding us. And you can see the numbers appear to be quite high, and I'll hopefully help you understand exactly what this means in a couple of slides here. From the air around us, again, there's radioactive gases continuously surrounding us, being breathed in, and so on and so forth. And from our diet, potassium-40 I mentioned, from certain foods, and as well as other atoms that just permeate evenly throughout our environment. And then everything we stand on and walk through also contributes to our overall dose. But not all radiation is made the same. Here I illustrate the 3 different types, 3 largest classes of radioactive emissions, if you will. There's an alpha particle decay, a beta emission, which is the same as an electron emission, but from the nucleus, and there's also gamma ray emissions. And when it comes to the the ability of this radiation to permeate matter, alpha particles have the lowest ability to move through matter, and that's because they have such a high mass. They are quickly stopped, much like throwing a large object through a brick wall. The brick wall will do a fairly good job at stopping it. Whereas you go smaller and smaller, such as beta particles or gamma rays are actually photons, they pass through this matter much more readily, and so their penetration depth is actually much higher. When it comes to biological damage, because alpha rays are stopped, or alpha particles are stopped so readily, their relative biological damage is quite high. Whereas when you are dealing with beta radioactive decay or gamma, their relative amount of biological damage is much less. Now, it has more components to that, but that gives you an idea of the relative amount of damage done by each type of radioactive decay. And for iodine-131 and cesium-137, which we're talking about from Fukushima today, we're dealing with beta irradiation from those particular isotopes. Okay, so radioactive decay, just to clarify things, perhaps you've heard some things in the news. Typically, a disintegration per second of a radioactive emission, if you will, perhaps a little bit oversimplified though, is defined as a becquerel. This is one alpha particle emission per second, one beta particle emission per second, or one gamma ray per second. One disintegration, I am equating that here to one radioactive emission. So I'll leave it at that for now. But when it comes to dose, I mentioned alpha particles are stopped more readily. They do a lot more damage. So 1 becquerel of alpha is actually much higher in dose than 1 particle of beta. And so that is measured using the units we call sieverts. And so sieverts is the one that may have made the news recently, and it is weighted to the particle type that you heard before, as well as the intensity and duration of exposure, to give you some form of measure on the biological damage that you're doing to the organism you're looking at. And so that there hopefully will help you understand that we're not talking about radiation doing the same amount of damage regardless of where it's coming from. How does radiation damage you biologically? There are two basic forms: direct interaction with the cellular DNA or indirect interactions with cellular DNA. Direct causes strand breakage or base pair mutations or decouplings in DNA itself. So you see examples here of alpha, beta, and X-rays, or one could classify this as a gamma ray as well. Indirect damage is caused by the radiation interacting with matter surrounding your DNA, such as a water molecule, causing the water to split into what we call ion pairs, and then the ions then, or the free radicals, if you will, go on to create damage to your DNA as well. So your body has become quite adept at fixing the damage of these forms caused by the radiation that we receive all the time. And as you saw in the previous slide, we have hundreds of thousands of interactions with radiation every living moment. Okay, so what happens when we receive certain doses? When we live here in Vancouver, we receive roughly 1 millisievert of radioactive dose per year. Okay, so that's hopefully puts things here into this perspective for the rest of this these numbers here. So 1 millisievert per year just by living in Vancouver, 4 millisieverts per year by living in Calgary, and 50 millisieverts per year by living somewhere in Iran or Western Europe. And so we're well in the range here where there is no established biological effect to that exposure. And in fact, the Fukushima emergency workers were limited to a 250 millisievert dose to perform their duties. And so there is no recognized biological effect for receiving that dose. Now, once you move beyond that, some people begin to feel nauseous, and the effects of what we call radiation poisoning begin to show. So you have blood effects caused by bone marrow mutations and so on and so forth. And that's in the range between 250 to 1,000 millisieverts, or 1 sievert, if you will. And so the reason why people start to feel nauseous is because some of the more rapidly dividing cells are more readily affected by these doses of radiation. And so the lining of your digestive tract is comprised of rapidly dividing cells. And so nausea kicks in, and the symptoms that are described here also start to demonstrate. So beyond 1 sievert, you have between 1 and 3 sieverts where you start to really show real radiation sickness, and then there's another range between 3 and 6 sieverts where you begin to show loss of appetite, pretty severe digestive tract effects, and then your skin begins to become affected as well, and death can become likely if without medical intervention. Then between 6 and 10 sieverts, the symptoms are quite extreme, and then above 10 sieverts, you can expect that death is probably imminent. Now, you can see that even in Fukushima, in the plant itself, the radiation workers themselves, or the plant workers, are very far away from receiving the doses that classify radiation poisoning here. So the bottom line is, when it comes to dose, though, it's all a matter about the type of radiation that your body is being bombarded with, the intensity of that bombardment, as well as the amount of time that you're exposed to it. So when you hear from Fukushima that the radiation workers were exposed to radiation levels of 1,100 millisieverts per hour, well, if they were only there for 30 seconds, they didn't get 1,100 millisieverts. They only got 30 seconds worth of that 1 hour's total exposure. So that is how you control the amount of radiation dose you get when there is a significant field around you. Now, for all the rest of us, I wanted to highlight for you that you've already heard that cosmic radiation, terrestrial radiation, and atmospheric sources all around us every day contribute to roughly 2.5 millisieverts of dose per year. Within your own body, there are sources of radioactive isotopes that give you another 0.4 millisieverts per year. Sleeping next to your loved one every night can contribute about 20 microsieverts per year. And living next to a nuclear power station can actually contribute less than your loved one when it comes to the amount of dose you receive. Coal-fired power stations also contribute to your national, your yearly dose, and things like the granite, the U.S. Capitol building can actually submit or give you quite a bit of dose. And everyone knows that airline crews are regularly bombarded by higher levels of radioactive or radium or cosmic rays, if you will, and their dose is roughly 9 millisieverts per year. And smoking is a big one, can contribute up to 13 to 60 millisieverts per year through the contributions of polonium-210 that's present in the cigarette smoke. So the maximum acceptable dose to anyone in this room, should they happen into a radioactive field, is 1 millisievert per year. And this is the dose that defines the consumption intakes you'll see later on in my presentation. For people like myself and others at SFU that work with radioactive materials, we're allowed to be exposed to, on average, 20 millisieverts per year on average over a 5-year period. So we can actually get 50 millisieverts one year, as long as the next 4 years allow us to average out to about 20 millisieverts per year, and so on and so forth. Once again, the dose limited to the Fukushima emergency reactors, emergency staff is 250 millisieverts per year. So the two isotopes you've heard about, iodine-131 and cesium-137, I've listed others here because in the various sources I've seen other isotopes discussed. But iodine-132, which has a half-life of 2.3 hours, would have long since decayed away before it traveled across the Pacific Ocean and landed in Vancouver. But iodine-131 has a half-life of 8 days, so it was possible for it to make its way over to our shores. There's a big difference, though, between the half-life of the physical half-life of 8 days and the biological half-life, which is 120 days in humans. And so you saw Kris allude to that with the uptake of iodine and the sequestering of that iodine. The biological half-life is much longer. So really, essentially, the dose that you receive from iodine is based entirely on its physical half-life, since once you obtain it biologically, it's held within you. And here's a silhouette of an image of a human being that has ingested on purpose iodine-131, and you can see that their thyroid gland has become a source of accumulation for that iodine. When it comes to eating iodine or breathing in iodine that we happen upon, you can see that our actual intake limit in becquerels, not sieverts now, in becquerels, is 1.1 million becquerels. So you can see you're actually allowed to eat and breathe in quite a bit of iodine. And for cesium, which is a 30-year half-life, you can, because it does not locate itself in organs like iodine does, you can actually consume much more of it, 3.7 million becquerels. And the biological half-life is similarly just as long as iodine. So because cesium has a somewhat uniform distribution throughout the body, you don't have as much of a risk, so you can actually eat more cesium than you can iodine. When it comes to Canadian guidelines for the consumption of nuclear or radioisotopes in the event of a nuclear emergency, you can see here that there are a number of guidelines listed in becquerels per kilogram, and this is for milk and for drinking water and then other commercial foods and beverages. So I would classify Kris's, unless you go down to the Burrard Inlet and drink the water straight out of the strait there, or out of the drain water that fell out of the sky, that could be construed as your public drinking water. Now, thankfully, when it worked its way into our reservoirs and eventually into our taps, the iodine-131 has not been detected from what I've heard. So, unless you were drinking the rainwater, this is our this is our uptake limit or consumption limit for iodine-131 in that water, 100 becquerels per kilogram, and you can see already that we did not come close to that amount in the measurements that Kris made. If you decide to go and have some sushi in which the seaweed used was from the Burnaby Mountain or from the Burrard Inlet, then you now have the allowance of eating up to 1,000 becquerels, and that's because the assumption of the amount of seaweed you eat versus the amount of water you drink and so on and so forth all contribute up to a maximum, if you remember, of 1 millisievert to an individual. So there's another level here that I'm not talking about, which has to do with consumption of radioisotopes in a non-nuclear emergency, and that's actually 1/10 of what we see here. But once again, you can see that we are not dealing with a significant source of iodine-131. One could argue that unless you're drinking rainwater, you've exceeded the 1/10 threshold. We have definitely not exceeded this threshold here. So I highlight these points right down here in this point. So for the rainwater, if I'm not mistaken, I saw 14 becquerels per liter, and for the seaweed, it looked to be about 400 becquerels per kilogram. To close off, I wanted to mention because of my specialty in medical imaging and radiotherapy, that we are continuously exploiting the benefits of radioactivity. And if anyone you know or yourself has ever had cancer, it's quite likely that they underwent external beam radiotherapy, or in some cases, brachytherapy. And it should be noted that when undergoing treatment with these particular medical procedures, that the tumor, not the patient, the tumor is receiving up to 10 sieverts per week, or up to 40 sieverts per week for the brachytherapy, and these are actually surgically implanted inside the patient. So you can see that if this was an entire human being, it would be a lethal dose. What we're doing here is we're actually exploiting it for the benefit of curing or getting rid of harmful tissue within the human body, and with no effect to the body as a whole. So high doses of radiation can be beneficial as a whole when focused and used appropriately. So in summary, the radioisotopes released from the Fukushima nuclear reactor do not pose an imminent threat to North America at this time. We'll have to continue to monitor the situation now that they've raised the alert level from 5 to 7. We'll have to make sure that we pay attention to what's going on over there. The radioiodine levels measured in Burnaby and Vancouver didn't exceed Health Canada's action level, but we'll have to, like I said, continue to monitor the situation, and of course our thoughts go to the Japanese people and their recovery effort. And with that, I want to thank all of you for your attention, and if there are any questions in the future, I wanted to warn you that my hearing isn't good, so please speak up if you have any questions. So thank you.
Well, thank you to all our panelists for engaging talks. I'd like to open up the floor now to hear from you. And as I mentioned earlier, this is a very important part of this engagement process that we're attempting here. So please feel free to ask any questions or concerns that you have. We'll address them generally, and possibly one or two people will take the lead on that. We have 2 microphones, one on either side. So I just ask if you could come up to those microphones to address your question, and we'll take questions now if anyone has any comments. Or thank you.
Yes, hi. Name is William Gibbons, and interestingly enough, I was at SFU last year at a conference called Foreign Policy Camp, and it was young Canadians from SFU talking about Canada's foreign policy. And I proposed a session on the heels of our medical isotope production scandal in Canada on Canada's nuclear policy and our foreign policy related to nuclear development, of which I have certain concerns. Setting aside any of my particular bias, it was interesting to note that nobody came, which is not unusual in my events. But what did occur was after this conference, which was being heavily monitored by the feds and other political entities in Canada, there was a slate of articles on Canada's nuclear policy. The most interesting one was medical isotope production at Triumph. And I actually mentioned this in my talk, was that Triumph had proposed a cyclotron solution to the production of medical isotopes. And in my opinion, this was an example of the heritage of international cooperation and collaboration and scientific endeavor, which addressed serious questions of whether we needed reactor-based production of radioisotopes, which also Triumph offered that technology as an open technology without patents or restrictions or commercial limitations to anyone that would develop a viable technology to address these international needs. So I think in some ways, Triumph has led the way and set an example for the world. But I would like to ask all of our panelists whether Canada is failing in its international nuclear policy, in particular the shortcomings that we see in Japan with the mix of privatization and the private corporation and government information. I mean, Harper's refusal to measure milk at the request of Canadian milk producers is one thing that I think is of concern to Canadians. The privatization, the costs, the subsidies, the insurance issues you talk about. Oh, if only economists could be as sure as the thermodynamicists and the physicists.
So your question is on the Canadian policy around...
Yes, I think that it's a challenge to Canadians and to academics to develop technology and solutions, whether it be energy, medical. For example, the scandalous scans issue in BC, where they can't even analyze them, and people are being exposed and they're not even getting a proper diagnosis. This is a failure of science, medicine, public policy, health policy, everything else down the line.
Okay,
Canada has a lot of self-examination to do.
Thank
you very much.
So the question is about policy in
Okay.
Canada.
So for a little bit of background to the audience, there was a competition last year for $35 million worth of funds for to explore technology to produce in an alternative fashion medical isotopes for the medical community. So Triumph, with myself as one of the principal investigators, was awarded $6 million to bring this technology to fruition. So the technology we're talking about is using accelerators. And just to summarize the background here is we have Canada's medical isotope production reactor in Chalk River, Ontario. Was shut down unexpectedly a number of times between 2007 and 2009. And it is that spurred on this competition. So from there, people should also know that 2 other reactors were built to the tune of a couple of $1 billion. The Maple reactors, they were called. And their intention was to be used as a medical isotope source as well for the world. They could actually, in theory, produce enough medical isotope to produce the world's demand twice over. All right. So those reactors were never started. And there was some complications there associated with turning them on, and the behavior of the core was not what was predicted. So I'll leave it at that. So the Safety Commission said that I'll say this, but I mean, if you get the right people in the room, you'll get quite a conversation going. That the Safety Commission said, if you don't fully understand how these reactors work, you're not allowed to turn them on, and that's my opinion, and I'll leave it at that. So, getting to the point of the question, then the policy has since from the government evolved so that we are pulling out of the nuclear reactor for medical isotope production business. We'd like to privatize it, and here is some money to pursue alternative technology. So here we have 40 years of history of producing this medical isotope that's used in over 40 million scans around the world every year. 85% of it could potentially come from Canada, roughly 40% does. And the government wants to pull out. So how else can we make this isotope? And that's where Triumph has been asked to produce the same isotope using accelerators and not nuclear reactors. So the problem is that with 40 years of regulatory approval and safety demonstrated, can't just change it. Health Canada, the FDA would have a lot to say about that. So we're working through that right now. We've been given 15 months to spend our $6 million and demonstrate the ability of this technology to produce the medical isotopes in question that they are produced in an identical fashion and behave in an identical fashion to the isotopes that are produced in Chalk River. So.
Thank you. Mark?
I can't speak specifically to this, but it does raise a broader issue that I would like to speak to. And that is, so there's an issue of whether or not public or privately owned and therefore regulation coming, of course, from some entity or agency of government, whether or not one will lead to better chances of safety and security than another. And I don't think the evidence is as clear as one might hope to say, oh, well, let's all run it publicly, as the Chernobyl was run publicly. I mean, it all depends on how well you do with your institutions and your incentives for effective regulatory coverage of whatever activity it is. Now, we all, though, have this, or all entities have this thing that political scientists study called regulatory capture. And it doesn't really mean that the regulator is captured, but it means that in some ways, during a period of regulation, you get more influence by the people you regulate, because they have a lot of motive to win you over, to convince you that they can take care of things on their own. And if there's been a long period without anything going wrong, there's a certain complacency that sets in, and regulatory standards can become more lax. And this will happen in just about any kind of regulatory setup. And it can lead, it can contribute to things like the BP oil spill in the Gulf that we experienced in the last year, or Fukushima, or 3 Mile Island, or other kinds of incidents like this. And I think one of the real challenges that we have then is to look again at our different energy options and say, okay, if we know that regulatory capture is likely to happen, and so something bad will happen, that bad thing happening in this one of our energy options, how bad can it be compared to this other energy option? And I think that's something that nuclear has to really worry about, so that regulatory capture with nuclear can lead to some very bad outcomes. So on that global energy assessment I'm on, our key lead author is in nuclear is Frank von Hippel, who was at the senior levels in the US government in the Clinton administration and has been in various international organizations. And he wrote an article in the New York Times shortly after Fukushima on regulatory capture, which I recommend if you're interested in this issue that you hunt down, or I can help you find it.
Great, thank you. We have another question over here.
I have laryngitis, so you have to excuse. I have a couple of questions. My name is Birgit Schröder, by the way, and I guess I'm what the Anglo-American press refers to as a nuclear-phobic German, because of having been in Germany after Chernobyl with 2 small children and the government stuff that went on then, and especially in France too. So I'm very eerie when it comes to nuclear accidents, right? So there's different numbers for Chernobyl death, right? The WHO states between 4,000 and 10,000. Other reports call it up to 1,980,000 or so, depending where you look at. And it's all doctors and scientists, putting their names behind these numbers. Nobody knows. Regarding monitoring, I have a question which is, and if you like some background names, I have them with me according to numbers. Is it the SFU monitoring, was this a one-time in 3-location event, or is this ongoing?
I think we started monitoring before Fukushima with the intention to monitor the Fukushima releases. We are not, our mandate is to do research, not to do monitoring. And there are governmental agencies which are in charge of doing monitoring. We took it as a research project. I think that on the regular basis, I don't see a research benefit to it. I think that there are monitoring stations in Canada, in North America, which are associated with the comprehensive treaty on the nuclear weapons, right, which are doing these things. Although if there is a need comparable to that, we are capable of doing that, right? I mean, we are capable of doing environmental monitoring.
But it's not your mandate.
It's not our mandate,
So,
and I think it will depend. It's a question of priorities, right?
Well, no, I'm not criticizing your work. I only wanted to know
Mm-hmm.
whether what we saw was one-time monitoring results or whether it's ongoing. So it was a one-time?
It was a
fair to say?
one-time, but if there is another crisis like that, I will most likely do this again.
No, it's fine. Because you mentioned the CTBT organization, the Comprehensive Test Ban organization, treaty organization that has, God knows, 88 working measuring statements around the world, right?
Right.
And I've been monitoring the news coming from Zentralanstalt für Meteorologie und Geodynamik in Austria, the ZAMG organization, which puts up reports every day in English based on CTBTO data. And the main scientist there too, sorry, I'm bad with names, but also says currently still not a major concern, health effect. However, he also points out that the data, especially for iodine, is incomplete because at those measurement stations only particles are monitored, not the gases. So there is measurement concern from scientists, renowned scientists, I guess, it's on the website, so you can read it up, who are not happy with CTBT organization measurement results that are passed on. And furthermore,
we measure everything which falls down in the rainwater.
In the rainwater, yes. That's why I was very interested to know whether you do it ongoing like the CTBTO does, to see, in terms of, because they do computer simulations.
So we have the access to this data.
Right.
Yeah, we can cross-correlate.
Right, and then on the for the weekend, the Norwegian NILN. Atmospheric, they in combination of CTBTO results mapped out the weather impacts and had, for example, called for this weekend for the West Coast a medium fallout, a higher than before because of current weather conditions. Do you know anything about that?
Yes, because I'm receiving a lot of emails with people who are very concerned, and our students have. Rachel came to the lab on Saturday because somebody sent me an email that there is a lot of iodine-131 coming over the weekend. And we're very disappointed to measure 0. One of the points which I showed was from this weekend. There was no iodine-131. So my students came to the lab, especially to monitor 131 iodine. There was nothing.
Was there another question?
Yes, I have one more, and which is right now published on Reactor. Radiation risks from Fukushima no longer negligible. It's from today, out of France. And whereas they mainly talk about Europe, they they talk about the results found in milk and in leafy vegetables and foods, which internal radiation is apparently worse than just external. And call for risk groups such as pregnant women and babies not to drink milk and or water that comes from reservoirs rather than deep from the earth. And they say based on radioactive nuclides found in milk and in the foods, and said that in North America the amounts found were 10 times higher.
10 times higher than what?
Than the European findings. Now my question is, does anybody here in Vancouver or in area test milk, grass,
the answer
etc.?
Is yes.
And where are those results?
These results are posted on the Triumph's website. Triumph measured the content of iodine-131. I mean, iodine-131 has not been detected in milk tested by Triumph. You can correct me if I'm wrong. And you can look, if you look at the content of radioactivity in milk, you will see a lot of decay of potassium, which is much stronger than any signal from iodine-131. So I think that this data, if you look into the Triumph website this data is available. I can give you the link also.
Paul, did you want to?
Yeah, and I'm just adding to the point too. In the immediate vicinity of the Fukushima plant, 157 food samples were taken yesterday, and only 4 demonstrated elevated levels of iodine-131. There were 3 samples of mushrooms and 1 seafood sample. So the milk supply in Japan itself hasn't been affected yet. So.
If I can add to that, I mean, this is not the first time it happens. I don't know if you were here around 1986, but actually there are documented measurements of seaweed from Vancouver from 1986, where the levels of iodine-131 in seaweed in 1986 from Chernobyl were 10 times higher as compared to the levels which we are seeing now. The other studies which are published are the studies from Nagoya, Japan, where people were measuring rainwater after the Chernobyl accident, and they've seen 4 times higher levels than we see, and they follow up, and essentially with the conclusion that there was no impact on the population from this. Moreover, I think that one of the questions, which is a very difficult question, and it's a very controversial question, is a question of low-level exposure. Okay, and the reason this question is controversial is that it is very difficult to put your hand on the hard data on low-level exposures. Low-level exposure is very difficult to quantify. It's very difficult to trace. If you look into the spectrum of opinion on the low-level exposure, you can pick up whatever you want. So whatever you believe, you will find justified by sources. Okay, the reason I'm talking about it is, as Paul was showing, one of the arguments of the low-level exposure is that the argument that the dose, internal dose, right, that this is the iodine-131 gives you an internal dose. You need to remember that you have carbon-14 built into your body, and carbon-14 gives you the internal dose. And we calculated that 1 kilogram of dried seaweed gives you 10 times less dose than the carbon-14 in your body. So you need to eat 10 kilograms of radioactive seaweed to get the internal dose equivalent to the carbon-14 dose from your body.
Well, you know, because I'm not a
Sorry,
scientist.
we have a number of speakers. Maybe we could carry on. We have a question over here.
Hi, Tim Takaro with the Faculty of Health Sciences at SFU. I had a couple questions. One was the fact that the crisis is not over, and I wondered if the panelists might comment on the increasing risk that the IEAE is, or IEAA, International Agency of Atomic Energy, has increased, and why they have been increasing that risk level. Perhaps you could answer that, and I had one other follow-on question.
So from what I read this morning, the dose rate immediately surrounding the Fukushima plant was measured at 2.2 microsieverts per hour. And so that's per hour. When you consider in Vancouver we get between 1 and 2 millisieverts per year. So you can tell we're not at a dramatic increase in dose rate immediately surrounding the Fukushima plant. My guess is for the elevation of severity from 5 to 7 recently, and this is literally news to some of us as we were walking into this room, is that they perhaps found a level of contamination that they didn't expect. And then what they want to trigger is a public awareness and the subsequent expert monitoring in order to make sure that no one is inadvertently exposed to a harmful level of radioactivity.
So it was not related to today's earthquake. There was another 6.4 Richter earthquake around Tokyo.
Yeah.
It's not related to that.
I mean, Corina may be able to comment more on this. I believe the plant is in a stable as it can get at the moment state, as long as power is supplied to it. Power was lost during the most recent earthquake, but it was restored also not too long afterward. And I think the level of release we saw with Chernobyl would be difficult to achieve here. But Corina, I don't know if you have more to comment on that or not. So.
I think they somehow stabilize the situation, but the situation is still can develop in a way that we cannot foresee. So they are ultra cautious. Probably there is a lot of pressure. There have been a lot of I just had a glimpse at the level 7 severity of the accident. So they said that the radioactive release was higher than initially thought, and the people have been evacuated. So it's considered a higher risk. And as I mentioned, to cool down the reactors, it will take a lot of time, so things can change rapidly. There will be, they expect aftershocks, and they have to monitor everything very seriously. So other than that, we have to see what's reported from there.
You had another question?
Yes, this was related to MOX fuel, the fuel that contains plutonium and highly enriched uranium, which the plant number 3 has, I think, 6% MOX. My question relates to a program that's pushed by the United States to increase the MOX or the plutonium content in MOX fuel as a proliferation reduction or proliferation risk reduction mode. So fuel that is being developed in the U.S. is meant to be up to 30% plutonium. I'm wondering if perhaps, Mark, you might comment on the viability of MOX fuel as this future evolves in the context of the Fukushima, considering that had there been a complete meltdown in number 3, there would have been a release of plutonium.
Yeah. No, I'm not qualified to comment on this. I mean, you know, this will be how do any of these kinds of extra risks factor in all along the choices, and I know that's where the big debates are in the whole issue of fuel reprocessing, fast breeder reactors, and so on. And it's been going on since I was a grad student. But I can't really comment on this particular choice right now.
Any of the other panelists have a comment on the future of MOX fuel?
The only thing I've heard is a movement towards thorium-based reactors. This is a whole other culture that's open for debate. I believe uranium-233 is another one, and again, I'm stepping out of my expertise here, but I think there are headwinds on all of them, and I can't even begin to imagine I could answer economic questions.
Both of those, the thorium and the uranium-233, would be lower proliferation risk, right?
Oh, okay.
I'm asking.
I'm unsure. Yeah, I'm not sure.
Yeah, I don't know either. I've only seen the thorium numbers just because of fuel shortage concerns.
Thank you.
Thank you. You had a question over here? Actually. Oh, sorry.
If I could actually answer some of your first questions. I, along with my wife, who is Japanese, monitor the Japanese media directly. And the reason the Japanese government is considering elevating from 5 to 7 is that, and this was just reported probably an hour or two ago in the Japanese, several hours ago in the Japanese media, so there's some translation lag, is that they decided that the amount of radiation that was released in the initial period after the accident occurred was quite a bit higher than they thought. And so, if anything, it's a historical revision rather than any reaction to something that's happening now. On the subject of the the most recent earthquake, and they're having earthquakes of 5 to 6 magnitude daily. So you don't hear about it if it isn't at least 7. Keeping in mind that the earthquake in Christchurch was approximately 6.0. This is an everyday experience in Japan now. The 6.2 magnitude earthquake several hours ago and the 6-point-something magnitude one several hours before that caused no damage to the plant. However, what it does do is it makes everything shut down. Everybody has to leave the plant. The power stops. And then they have to start it over again. So this does cause delays and issues. But in terms of damage, like direct damage to the plant, there has not been any. But it's a good thing too. They don't need any more. But thank you. Sorry for the
no.
Yeah, great.
So
Thank you.
I just run on Google what's a level 7 accident, and Fukushima, and there are not enough articles yet released, but level 7 accident is a major release of radioactive material with widespread health and environmental effects. So probably they are concerned about what's happening around Fukushima and some of the level of radiation released immediately after the earthquake.
And so, as you pointed out, it was a historical revision of that caused that. Okay.
Chernobyl was 7?
Yes.
Yes, but if I can comment? I think that one thing to recognize was that Chernobyl, the explosion of steam in the Chernobyl actually exposed the core, right? And the chemical fires, they used graphite as a moderator, so it was an explosion which exposed the core combined with the chemical fire, which related in the distribution of a fraction of the exposed core into the atmosphere. That didn't happen, right? First of all, there was no graphite, it was only water. I think that the leak of the water might have contributed to that, right? The leak was stopped. So I think that, I don't want to comment on the assessed severity of the accident level, but I think that I still would say that compared to the Chernobyl, the releases would be factor of 10 or 100 smaller. There's no way they can be with this scenario so far.
So a low 7 versus a high 7.
Well,
Okay. All right, we have a question over here.
I actually have two questions. The first question is regarding the seaweed. So I was wondering about, and first of all, commends for actually undertaking the seaweed measurement program. I think that was an excellent idea. I was wondering about your sampling strategy and the methodology that you used to collect the different samples and why the Bamfield samples were actually lower than the ones that you found in North Vancouver. Was that reflective of the kind of seaweed that you were monitoring at that point in time?
No, so that's a very good question, and we are working on addressing this question, and Anne, who's here in the audience, also contributed with collecting samples of different seaweeds which we are measuring. I think that the accumulation of seaweed, it is specific to kind of seaweed which we are measuring, but both Bamfield and North Vancouver were fucus seaweed. And I think that so the bioaccumulation should be similar. I think that it is essentially it's the correlation with the amount of the fresh water the seaweed is exposed to. So I think that they come from different places, and we have now we suspect that essentially the location of the where we take the samples from North Vancouver is exposed to more rainwater and freshwater accumulation than the Bamfield samples. What we do is we collect wet seaweed and we dry it and we dehydrate it and then we grind it and then we put it on a germanium detector. We do the same thing for every species. There's nothing more specific than that. I don't know what else should I.
No, that's great.
Okay.
The other question is, it's along the similar vein, and I know that Canada has been monitoring the cesium levels in caribou tissues after the bomb testings that was done in the 60s and 70s. And given that First Nations people and northern communities are often disproportionately affected by contaminants such as radioisotopes, is Canada at all considering a monitoring program in the north or something going forward looking at First Nations people and their diet and what the impacts may be?
So we were contacted by a large number of First Nation, either members of the First Nations or officers who are working with the First Nations, and some of the samples were sent to us by First Nations. So I think that I don't know about the monitoring in the north. I cannot comment on that. I think that the samples which we measure, they vary. I think that Fukushima is actually collecting the most, that's the reason we do it. I think that the levels are lower, in general, lower than 400 becquerels per kilogram of dried seaweed, and and they will be significantly lower. So some are like 50 becquerels per kilogram. It will depend on the location and the content of iodine-131 in the rainwater. In regard to cesium, we right now are focusing on iodine because it's a short-lived isotope. So we want to get as much done before it decays, but we save the samples. And then we can re-examine the samples. Cesium-137 has 30 years half-life, so we can, when the releases of iodine-131 are gone, we can then go back to the samples and remeasure with much longer exposure times for radioactive elements which have longer half-lives, which we are intending to do.
And will you make that publicly available, the data?
Yeah, we will make it publicly. I mean, at the end we would like to publish it in a form of scientific paper, but sure.
Great. I look forward to that. Thank you.
Are you continuing to sample now?
We continue to sample. So of course the rainwater depends on the weather, and we continue to sample the seaweed. Although if the trends will go down as they do, at some point we'll probably have to stop because it is a significant effort.
You're one of the only people in Vancouver hoping for rainy days. So we have another question over here.
Mine isn't a question, it's a comment. My name is Mitchell Halpern. I'm from Toronto. We don't have any ocean water that comes near us. I'll just tell you about an experiment that happened by mistake in Taiwan. They were building apartment buildings quickly. They ran out of structural steel that was the kind they wanted that wasn't contaminated. They then built apartment buildings with steel that was contaminated with cobalt, which was an alpha emitter, which is a much more serious one. Emitter. Now, the outcome measures that they measured weren't levels in water or whatever. They measured the incidence of malignancies relative to the control population that were living in the same areas, but not in the apartment buildings with the contaminated cobalt. And the incidences of all the malignancies were less in the group that lived in the cobalt-contaminated apartment buildings. And if you want to Google it, you just type in radioactive cobalt Taiwan, and you'll pick up the first author's name is Chan.
Could you comment on that?
Yeah, absolutely. Thank you for that comment. I think what we're witnessing is there's some controversy around this, but we're looking at a net benefit effect here, where it is believed by some that a small dose over a long period of time of radiation actually has a net therapeutic effect on individuals. And for similar reasons, you can look up studies on residents of Arizona where they have higher levels of radon in their basements. Radon is the best thing that ever happened to smokers because it kills off pre-malignant tumors in their lungs. So thank you for that comment, and I believe it's quite true.
And I think that gives an example of some of the complexities of calculating this risk. Sorry, we have a question over here.
Thanks. I had a couple of questions. The first one was to do with the measurement of radiation dose and the biological effects, that being the sievert or the millisievert. It seems that that's basically a unit of energy, right? And factored in with a biological absorptivity factor.
It's joules deposited per kilogram of tissue.
Shouldn't we also, and I'm sure people do, but I don't see anything about this in the media, shouldn't we be looking at something more like power, like dose rate, I guess? If I get 1,000 hours of sunshine over a year, that might be a healthy exposure, and I get lots of vitamin D. But if I get that same energy in a minute, then I'm dead, right? So when they say 50 millisieverts a year is a safe dose, surely that matters whether you get it evenly over a year or over a second. Am I right in that?
You're absolutely right. So if you recall my slide, it said that you have the type of radiation, the intensity, and the duration. And so that's what you're referring to there is the duration. So the Fukushima emergency workers were allowed to accept doses up to 250 millisieverts per year. but they could have received that dose in 5 minutes if they were at the right place in the plant. So you're absolutely right. You have to pay attention to duration along with intensity.
Because the examples you kind of see in the media, so it's like an X-ray is 2 millisieverts or whatever, but it doesn't seem to factor that in at all, that kind of the effect of the intensity of it.
So I'm not sure.
X-ray is pretty quick.
Sorry?
X-ray is pretty quick.
Yeah, exactly. Yeah, yeah. Anyway, the other question I had was around this division between internal and external emitters. So with things like iodine-131, which doesn't occur naturally and is an alpha emitter, I think, being absorbed right into your system and emitting over a long, well, actually in iodine, not that long, but in other things like cesium, a long time potentially. And whether, again, I'm just thinking of kind of media, what I see in the media, you see that compared to, again, like background radiation. A flight to Tokyo is the same thing, but these are different types of radiation and totally different circumstances. So is that a fair comparison or not, I guess is my question.
Another complex issue. So internal versus external, you're talking about implanting a radioactive source next to your DNA internally. Externally, you have the benefit of your skin and other tissue blocking the more of the harmful effects of ionizing radiation. So the issue is somewhat complex. So to answer your question a little bit, iodine-131 is a beta emitter, and it accumulates preferentially in the thyroid gland of the human body. And so this has certain biological health implications associated with it. So we've all heard about the Russian spy who was poisoned using polonium-210. This is available as anti-static brushes in photography, in the area of photography and whatnot. He probably ingested very little of that material, but because it was internal, the anti-static brush that went from being a piece of equipment you can use and being not harmful to being internal poisoned and killed him. So there's that's an example of internal versus external effects there, and there can be a big difference depending on what you're looking at.
So when we see these background radiation is so-and-so, which may be mostly electromagnetic radiation, and that's compared to, it's the same level of something that's going to be absorbed into your system and go on emitting over a distance of microns, right, for a long period of time. Is that a fair comparison, or is that really misleading?
Again, it's complex. So background radiation is coming from different sources. Radon is an alpha emitter. Cosmic rays are likely in the form of gamma or photon type emissions. So I don't know if any other panelists has something to add, but what we're looking at when you talk about a sievert or a millisievert or a microsievert, we're trying to normalize that effect. So basically, by saying we get 2 millisieverts per year from atmospheric interactions, and we get 0.2 millisieverts per year from terrestrial, and 0.4 millisieverts per year from cosmic, whatever it may be, we're trying to normalize.
So it factors that in.
Yeah.
Okay. Thank you. We have one more comment here.
I think that you need to recognize that you have radioactive isotopes built into your body. You have the internal dose from carbon-14 in your body is on the order of 4,400 becquerels. Okay? The internal dose from strontium and the internal dose from potassium decays in your body is on the order of few thousand becquerels. And it's all internal, and these are all beta emitters followed by the gamma emission. All right? So now if you think about the kilogram of seaweed at 400 becquerels, if you eat a kilogram of dried seaweed and you received internal dose of 400 becquerels, carbon-14 in your body is 10 times higher dose internally, prolonged over your lifetime.
Right. How much is a kilogram of seaweed?
It's a lot of seaweed.
Okay, we have another question here.
This pertains to fusion power. No, thank you for all taking your time to do this. My question is about how the boiling water reactor compares to other types of reactors. What proportion of reactors in the world are boiling water reactors, and how other types of reactors would have fared under similar circumstances as Fukushima, as the earthquake and tsunami that had just happened?
I can comment briefly. So there are different types of nuclear reactors. We have boiling water reactors, pressurized water reactors, heavy water reactors, gas-cooled reactors, and next-generation reactors. In Canada, we have canned reactors. In Japan, we have boiling water reactors. In the States, we have mostly pressurized water reactors. In the UK, they use mostly gas-cooled reactors, and they're researching, and there is research done all over the world with more or less success on different kind of reactors. These are the main types, and they come with pros and cons, right? And it also, for example, Canada has CANDU reactors because they decided to use natural uranium and heavy water as a moderator, right? So it depends on the technology available and the resources available and the economics of a specific country.
So there's pluses and negatives for...
Yes, there are pros.
How they fare in similar circumstances?
So they come with different, most of them, they have a similar features, but they are also distinct, right? It depends on the fuel, it depends on the moderator, and it depends also on the emergency systems. Other than that, they all have the same, more or less, features, right? CANDU reactors, they have this huge envelope which costs a lot, right? Boiling.
I think, sorry, we have time for one more question.
My name is Phil Walkinshaw. I have one comment and two fairly simple questions. The comment is, and someone mentioned about milk. On the Seattle News a week or two ago, Yakima, they checked the milk and they said there was radiation in it. And I do remember that because I went to Starbucks that day and thought maybe I would drink it black. And so I didn't see something similar about Fraser Valley milk, but I might have missed it. But it was definitely there, and there was definitely radiation. But that was probably in that March peak that your, testing showed. And my two questions, if I don't drop my glass here. The first one is this reactor that had the catastrophe. I don't know if it was an accident, it was the right word, but it's a 60s design developed by General Electric. Are the new ones being built today, are they safer and more efficient and better?
It's true, the Japanese reactors were built after General Electric design. They are built in the 60s. Units 5 and 6 are newer. Units 1 to 4, they were built in 70s. They are advanced boiled water reactors. They are more advanced, as the name says, but
are the newer ones more efficient, more safe?
Are they safer than newer ones, or could the same thing happen again?
Comment?
Yeah. Yes, absolutely.
I think that one thing which has to be recognized, right? It's very simple. You can build a structure around the reactor which will prevent it from, the direct heat of an airplane, right? You shoot an airplane on it, nothing happens. You cannot design the reactor to withstand its own heat. This is a cooling accident. There is so much heat in the reactor. If you don't take the heat away, it's going to melt. There is no way around it. The reason is that this is the heat you want. You cannot build a reactor and prevent it from doing things which you want. It's a failure of the cooling system which was not capable of taking the residual heat from the fission fragment to be taken out from the reactor. And that's why the thing has melted. It's a huge power. It's a few percent of the 2 gigawatts of thermal power. We are talking about megawatt, tens of hundreds of megawatts of thermal power.
Okay. Thank you. Sorry, we're just running out of time.
Okay, so. The heat is what produces to make the turbines run, to create the electricity, right? So in other words, the new ones are not going to necessarily be any safer or better than...
Hopefully they would be. Sorry, if you had one more quick question, and then...
And then I know it's getting late. I'm in the vehicle business, and I get asked all the time about electric vehicles, if that's the way of the future. And it seems like the presentation, we're either faced with global warming and climate change, or the threat of radiation. It seems like.
Well, I think generally there's the idea is that there are risks involved with energy production, and the thing that I've learned from listening tonight is that all of the sources of energy have their risks.
Well, what's the risks with wind?
The risks are around. Well, Mark can answer that.
Well, we don't know, but when we scale up wind, there's a lot of research going on right now about the effects of all of those wind turbines on movement of air and what that might mean. So it's like right now when renewables are a tiny part of the system, what we have to try to do is think about what the scale-up effects are. So we know less about them than we do about nuclear and fossil fuels, but there may be some risks there as well.
Well, there's certainly risk with the building of turbines and of the lubrication and of all the other aspects of wind. So there are risks involved.
But
yeah, sorry, we had just one more question here.
On? Yeah. So just apropos this question about the newer versus older, I was at a meeting, I guess, mid-March, where there were people talking about the plants, and the impression that I had was that the newer, pretty much right after these GE plants were built, GE started introducing, they shifted from active cooling to passive cooling, and as I understood that, they didn't go into detail, but as I understood that, that would have greatly mitigated the risk in this accident. Maybe you can comment on that. But the active versus passive, meaning that active cooling, you've got to actually have engines to cool it, to bring the heat out. And passive cooling means you've designed it so that it kind of happens automatically once the power goes out.
I think that a simple argument here is that if you had a tsunami and you have a debris, right, which block the intake of water, then you're in trouble anyway. I mean, you have to have water, and you have to have water circulation. Any disruption in the water circulation is a huge problem. I mean, passive is better than active. And the other way to do it is you can have thermal engines, right? You can have the heat being transformed into the mechanical work and taking the heat out from the core. It's all possible. The thing is that you cannot build it so it's 100%. You cannot predict all possible. I mean, you can predict, but you cannot counteract all possible risks, right? I mean, I think that's a combination here. It's clear there was a combination of the tsunami and the earthquake, right? That's the shutdown after the earthquake was clean. It was the tsunami which was taking the cooling system.
Okay, I think we have just time for just one more, and then.
Thank you. I'll be fairly brief. My question is mostly towards risk assessment and the ability to predict consequences. Given that we have apparently, according to the numbers given, approximately 440 nuclear power plants worldwide, I think we have a fairly glowing future ahead of us. But that aside, I wonder whether there's been a systematic risk assessment done to see, given the different natures of these nuclear power plants, their methods of operation, the kind of supervision that's happening at these power plants, when we can expect the next big one. If you do an assessment, a risk assessment, you can come up with these things and you can make some kind of prediction. And whether based on that prediction, it really is a worthwhile approach to energy generation.
Thank you. That's
and
the crux of the matter here. Yeah. And that I think Mark has something to say.
I don't know about the others, but yes, I've read a lot of risk assessments for nuclear and alternatives. And I guess so what you said, one thing in your comment, which was, I think you were saying that then once we took in all of the information that we had, even human failure and so on, that we would get a fairly accurate sense of what that risk might be. I don't know, or you were asking if that was possible. And I think, I hate to do this, but I may borrow a little bit from Donald Rumsfeld, who people may remember talked about the unknown unknowns. And this has been a source of irritation for energy analysts like myself who have over 2 or 3 decades dealt with nuclear risk assessments in which at least a lot of the people I had to deal with just didn't want to talk about the unknown unknowns. And so it was, here are all the things that we know can go wrong in a plant and under all the circumstances, and now here is, going forward on a planning basis, the likely probability of human mortality and morbidity per kilowatt hour generated of this technology. And I think we have to recognize that humans are not capable of predicting all possible outcomes into the future. And so that's why I'm saying you also have to kind of turn this away from risk assessment, which is the probability multiplied by some bad outcome, to also just looking at the bad outcomes and saying, what's the worst kind of outcome that might happen with this particular technology or option versus that one? And on that basis, you might turn away from one of those options, even though it was very expensive or there's some other nasty risks in the other direction. And on that basis, society could say, we just can't go with nuclear power. We just think there are the downsides associated with it. We may want to do some things to keep that option open in some way, but not in the kind of scaled up way that some of those scenarios that I was looking at. And it would be because of that kind of debates that we have about risk assessment.
Thank you. Sorry, I think Mario.
Well, I think this is a fine note to end on. Thank you, Mark. Ladies and gentlemen, I think you'll agree with me. This has been a very informative and engaging session. The panelists and the moderator have given freely of their time to be with you and to discuss the issues in a very frank and open manner. I hope you've enjoyed it. Please join me in thanking them for their efforts here tonight. Thanks again to the local section of the Chemical Institute of Canada. Vance Williams is its president at the moment. Thank you, Vance, for all your effort. And thanks to Simon Fraser University sponsoring this event. And thank you all for coming and engaging in discussion. Have a safe journey home.